Right. Hello, thank you. Can you hear me? Yeah, good. All right, so last time we finished by defining the SG2 and SO3 plus and SO3 minus theories. What I'm going to do next is study the generalized symmetries for these theories. So this time I'm going to start by describing the charged operators. So let's start with the SG2 theory. And in this case, we have a Wilson line. I have to tell you in which representation it is, so let me take the Wilson line in the fundamental. And as usual, it's wrapping some path. Right, so if you want to write this in terms of fields, this object has a standard description. It's very similar to what we saw before. In the Maxwell case, it's the trace in the fundamental of the exponential of I, the integral of A. The only issue here is that because we are in a non-abelian setting, you have to be a little bit careful when you define this object. So we put here a path ordering operator. And what this means is that when you do the expansion of this exponential and you get a product of integrals, you always order the operators A as they come along the path in the integral. Okay. Which ones of you haven't seen this? Have not seen this? Okay, you have all seen this, wonderful. And a bit more abstractly, the way I like to think about this is the trace, in whichever representation you have, of the holonomy of the connection over gamma. Of course, this is just if you want a definition of the holonomy, but I find this a little bit clearer to think about. What this means is that you take some charged object, you drag it around the manifold, and the vector in internal space changes. This is the precise expression that tells you how it changes. But geometrically, it's just how this vector is parallel transported around the manifold. Okay, so this is the Wilson line. And they exist in the SU2 theory. As in the Maxwell theory, we can view this as the insertion of a very massive particle that we are dragging around the theory and seeing how the theory responds. And this very massive particle is in the fundamental representation. So this is intuitively the effect of introducing a massive probe, so an object without dynamics, so a massive particle, sorry, an object without dynamics, so it's very massive, along gamma in the representation which we are given, in this case the fundamental. So we take a very massive object, we drag it along, and we see how our SG2 theory responds. Okay, so that's fine. That's something that you can do in the SG2 theory. In the SO3 theories, we can still sort of do the same, right? We can try to put a massive particle and move it in the theory. But remember that the thing that distinguishes the SO3 bundles from the SG2 bundles is that sometimes you cannot consistently couple some representations of SU2 to these bundles. Right? So in particular, the fundamental representation is a representation that cannot always be consistently coupled to SU3 bundles. What this means is that we can still define the object, but when it comes to SO3 bundles, it behaves as if we had in the Maxwell theory a particle with fractional charge. We cannot view it as a genuine operator, we have to view it as a boundary of some other surface operator. So again, it's useful to consider these open surface operators, but you have to keep track of the extension. So to keep track of this distinction, the word that people use is that the Wilson line, we say that the Wilson line is a genuine line operator. In the SU2 theory. But not in SO3. Okay. And all this means is that I can define this operator without ever specifying a surface in SU2, but if I try to define it in SO3, I have to tell you what the surface is that's attached. Or if you want, an alternative way of reading this is that this surface, if defined on a closed, if extended to a closed cycle, is always transparent in the SU2 theory. It measures something trivial. Okay, so let's think about this Wilson line for a minute. In the SU2 theory, the genuine operator, I will be thinking of genuine operators. If we have a Wilson line, we have a Wilson line. Nothing that happens to it. But if we have two, in the fundamental, then because in SU2 you have that the fundamental times the fundamental is that joint passes singlet, you can take two of these lines and they can end on sources, on operators that generate local operators. So in the SU2 theory, we do have adjoints and we have singlets, so we can break these lines. That means that the symmetry that in principle counts how many Wilson lines you have goes from being U1, potentially, had there been no breaking, into being a set 2. So symmetry counting Wilson lines, insertions of Wilson lines, is set 2. In general, what this symmetry will count is the net spin times 2 modulo 2. So how much half integral spin you have. Anytime you have integral spin, you can remove it by inserting local operators. So it's only the, if you want the spin of your representation, modulo 1, that matters, whether it's 1/2 or 0. Okay, so the general statement for any Lie group you can derive this with a little group theory, basically using this idea. The general statement is that the electric symmetry for simply connected simply connected G is set J. I'm taking a single factor and assuming that that factor is not U1. We have done U1s already, and if you have multiple factors, just multiply the centers. Okay? So generalizing this is not difficult. So if you want to see a proof of this in a physical way, rather nice paper that you can look at is the paper by Haroni, Cyber, and Tachikawa. It's called Reading Between the Lines, so it's 1305. Okay, so you can look at this paper, it's a very nice paper. It was written a bit before the generalized global symmetries paper, so they're not quite using the language that I've been using in the lectures, but by this point you should be able to translate quite easily as you read. All right, so let's do the same thing we did for the Maxwell theory. Yeah. Yeah, if I put two Wilson lines in the fundamental, so the first thing I should say, any representation in SU2, I can obtain by taking tensor products of fundamental representations. So by stacking this kind of Wilson lines, I can construct any other Wilson line, basically. Now, if I have two of these Wilson lines, then in their tensor product, there's adjoints and singlets. We have dynamical operators which are adjoints and singlets. So we will be able to construct, I'm not giving you details, but we will be able to construct open operators with dynamical operators on the boundary. You remember when we did the Wilson line in Maxwell with charge insertions? This would be analogous to the case of having a U1 theory with a charge insertion, a dynamical field of charge 2. So we cannot break one line, but we can break two. Yeah. Any other questions? Okay, very good. So let's think how we put backgrounds. So let me denote by set S2 tau B, the SU2 theory coupled to a background for B. Okay, in general, all we know about B is that it's some cochain of degree 2 in your manifold with coefficients in set 2. But in this case, we can do better. First, I'm going to take the boundary of B to be 0. As I argued in the lecture on boundaries in Maxwell theory, this will be, if it's non-zero, we are dealing with junctions, with networks, with boundaries. And this is the same thing as insertions of non-genuine operators. Okay. Remember the picture? At some point I argued that whenever your background field is non-closed, effectively the junctions that are generated in the background end somewhere. So in this kind of situation, we have our symmetry generator that generates the C2, and we have that at some point in a space, it ends on a curve. So what we have is a non-genuine line operator. In this context, it will be the Atoft operator of the SU2 theory, which is non-genuine. It's fine. We can construct the partition function in the presence of non-genuine Atoft operators, but let's not do that. Let's restrict ourselves to not insertion solvers. Okay, so that's one thing. And if I take this, then my BE goes from being a cochain to being a cocycle. Okay, that's easier to handle, definitely. Another nice observation, which is not obvious at this point, but I'm just going to assert it. This set 2 has no anomaly. meaning that the partition function of SU2 with coupling tau and background B plus some variation is the partition function of SU2. Again, I'm just stating this. One way to prove it, which is not immediate, is by trying to construct a lattice model of this theory that you can do, and showing that these gauge transformations can be done consistently in the lattice model. That is no observable depend on this gauge transformation. It's not an elementary exercise, and definitely not something I can do on the board. But it's not too hard to derive if you're geometrically engineering this theory in a string theory, for example. Or if you're doing lattice. Either way, let me just tell you that, okay? I found no easy way to explain this, so I'm just going to assert it. So these two facts together imply that set of SG2 depends only on the cohomology class of B2. Okay. So when I wrote this kind of expression, that's the general thing, but I could have written some brackets around B, and it will still be correct. All right, so let's try to give a bit more geometric understanding of what this background is. This is an electric background for the electrically charged objects. Let's go back to Maxwell. At some point, I argued that if you take the Wilson line and you introduce a background for the symmetry of the Wilson line, what I'm doing effectively is changing the quantization of F. Right? I'm summing over a different class of bundles, quantized in a different way. Now, we have some of that here. We have my Wilson line, which is a particle in the fundamental, and what I want to do is that as I drag it around certain 2 cycles, where I put the background, it should pick up a phase, it should pick up a holonomy. So imposing that the Wilson line picks holonomies on any 2 cycle sigma 2, dictated by the integral over sigma 2 of this cohomology class. Now, what are going to be the holonomies? This is a set 2 symmetry, so this has to be in set 2. So this implies, because this is in the fundamental, that what I'm going to do is to change the quantization of my SU2 bundles in such a way that they have this obstruction, the Stiffer-Whitney obstruction, precisely on those cycles where I'm turning on the background. So let me write the formula, and hopefully it will be clear. So set SU2 for some coupling tau and some background B to E, BE. It's going to be the sum over some topological sectors, the integral of the connection over the topological sector, e to the minus tau A and the other fields. But now the topological sectors, they get modified. In the standard case, I impose the topological sectors have W2 equal to 0. Here I'm going to impose that the W2 of my bundles is the class of B. Right? So again, the motivation, perhaps The clearest is that I'm imposing the holonomy has to be what the background tells me it is. Okay, and these Stifler-Whitney classes precisely measure the holonomy of lines as you move around 2 cycles. They tell me how bad do I have it, or which abstractions do I have to consistently define the path integral for an object in this representation, in the fundamental representation. But we also have the analogy with the abelian case, which in the abelian case, introducing a background for the electric symmetry was a change in the quantization of F. So I want to stop for a minute and make this analogy with the abelian case a little bit tighter, because I found it very useful in practice. So I'm going to change just for this board. I'm going to change my example to n equal to 2 SU2 super-Jamils. So this is the pure super-Jamils theory that you studied with Eli in the last few lectures. There was already a question yesterday. Somebody was asking, why am I doing n equal to 4? Everything seems to work the same if I do any other theories, and that's indeed true. I'm going to the SU2 case. The details are a little bit different, but the ideas are the same. But here I can do the following thing. I chose n equal to 2 because you studied it in the lectures. I could have done the same thing for n equal to 4. Well, you saw that for n equal to 2, you have a Coulomb branch. And you have 2 points in the Coulomb branch where something becomes massless. And the thing that gets massless are a monopole and a dion. Now I'm going to use conventions that, talking to Eli yesterday, I realized she was using different conventions than the one people generally use in this context. And so I'm going to use the convention in the second Cyber-Witten paper. So this is HepTH 9408099. So Cyber-Witten have 2 papers where they study pure super-Jamils and one where they put flavors. And in the first paper where they study pure SU2, they choose one convention for the electric charge, and in the second paper they choose a second convention for the electric charge. The one that makes the calculations I'm going to do easier is the second convention, in which they multiply the electric charge by 2. So this will differ from the conventions that you saw in Eli's lecture, in that you probably saw a 1 here. The reason I'm using these conventions is that if you look at the pairing between electric and magnetic particles, what happens to electric and magnetic particles as you drag them around each other, the ones that give you simpler formulas without factors of 2 are the ones in this paper. You use the formulas in the first paper, you have to put extra factors of 2 by hand. So not to confuse things and stay in the conventions I've used in the rest of the lectures, I go to this convention, which is, by the way, the more common one in the literature. Anyway, these are your 2 particles. You have a monopole and a dion. And otherwise, just the Maxwell theory. So I have a Maxwell theory. With charged particles. With charges generated by combination of these 2. So in notation I was used yesterday, combination of 0, 1, and 2 minus 1. Any BPS, let's say BPS. Any BPS particle in this theory is generated out of these 2 by taking basically bound states. Okay. So what this means is that I go from having a U1 electric cross U1 magnetic to a subgroup. So I have to see how much of this group is broken. Well, I have the monopole that breaks completely the magnetic U1. But the dione breaks only partially the electric one to C2. So this is broken to C2 electric. Now, this is not an accident. In any theory with a Coulomb branch, where you can go to some point in the space of vacua where you get a Coulomb description, you have to have agreement between the symmetries in that description, computed from Maxwell theory, and the symmetries in the non-abelian theory. The reason for that is that the existence of a symmetry is an operator statement. I'm saying something about the topological operators in the theory, and does not depend on your choice of vacuum. The vacuum is just a state. So this had to work. It's good that it works. So part of the reason why I have put so much emphasis during the lectures on Maxwell theories is that in practice, very often you can take your complicated interacting non-abelian theory, perhaps a non-trivial CFT, and very often you can go to a Coulomb branch, express in terms of Maxwell, and read the answer there. So this is a very powerful technique. Once you understand Maxwell well enough, you can do many things. So if you want to see a bunch of examples, you can go to this paper. You can apply this technique to many, many theories, including n equal to 4, but n equal to 4 is, for technical reasons, a little bit harder. By myself and Michele. All right, so let's move on. Either way, we have a set to electric that acts on these Wilson lines. I think we know. And let's reproduce again what we did in the case of Maxwell theory. Let's take the strongly coupled description and see what the symmetry looks like in there. So to go to the strongly coupled description, I use Montaigne and Olive duality. Any questions? Okay. So under Montaigne and Olive duality, in particular the S-duality generator, exchanges Wilson lines and Adolph generators. Okay, so this is sort of a general philosophy of these things. It always happens like this, but the details of how it happens have to be worked out. Again, to understand these things, I find it useful to go to Maxwell, but let me just give you the answer. So if you start with a Wilson line in the fundamental, as I have been looking at, you end up with a top line, and I'm going to call this H, sort of the fundamental top line, defined in the following way. So remember how we defined the original top line? What was it? You pick a line in space-time, and you impose that the integral of f around the line was 1. There's the fundamental top line, right? So similarly, we define something here, defined by imposing that the integral over some S2, which is linking gamma, so the picture is that you have gamma here and then some S2 here, and we are saying something about the integral of the fields here. The integral over this S2 of the second Stiffer-Whitney class of the bundle is 1. And again, you should think of this as the analog of saying that the integral of f is 1. This is essentially a characteristic class of the bundle. It tells you that the bundle is non-trivial on these two spheres. Just for SU2 and SO3 bundles, the thing that you can really measure on two spheres is just W2. Right? So we have the charged object, which is the charge generator, the operator that measures how many of these objects you have. Well, in this case, it's easy to write. Again, for Maxwell, the symmetry generator was exponential of integral of f. Here we have a symmetry generator, which is -1. So some symmetry generator on some surface, sigma 2. It's going to be -1 to the integral on the surface of W2 of the bundle. So clearly, if you put this operator around the top line, you're going to get -1. So it measures the charge of a top line. This is more or less by definition what the top line is. All right. Any questions? Okay, so let's continue. A standard procedure. We have symmetry generators. Let's put backgrounds of these symmetry generators. So a background, we call it BM, for the set 2 magnetic of SO3. Let me say plus, is a network without boundaries, if I want this to be closed, of insertions of this operator. Maybe we call it UM. So denote by gamma the cycle that the network wraps. Right, so I'm wrapping operators U, M on gamma. There's a two cycle. Is the picture clear? I have a network. Let me do it in low dimensions. I have a network. Maybe it's something like a line here. I'm wrapping this what gamma would be. And then I'm wrapping and putting operators U in here, and that introduces a background for the magnetic symmetry. The only difference is that I'm in 4 dimensions, so this picture should be 4-dimensional, and gamma itself is 2-dimensional. Okay, but this is the idea. You choose some cycles, and you put your symmetry operators on these cycles. That's gamma. Okay. So then I can just read the answer. What's the partition function of the SO3 plus theory for tau in the presence of some magnetic background? Well, it's going to be the standard partition function of SO3 plus. But now I have to insert these operators. What are these operators? They are -1 to the power of the integral of where I'm putting the operator, and I integrate W2 there. So this is -1 to the integral on gamma of W2E. And this is a bit more convenient to write this as sum over E integral over dA. Here both are closed, so I can use Poincare duality. So this is Poincare duality. Of -1 to the integral over the whole manifold now of Poincare dual of gamma cap W2 of E. Okay. So in writing these formulas, what I'm identifying is Bm with the Poincare dual of gamma. Right? Inserting a background means putting a network. The network is characterized by the geometry. So I'm going from cycles to cocycles. I'm going from gamma to Bm. So the identifications between Bm and the Poincare dual of the cycle. So I could also write this term here as Bm cap W2 of E. So that's the insertion of a magnetic background. Okay. Any questions? All right. Let me say something about gauging. This is not something I discussed too much in the Maxwell theory, and that's because if you want to gauge a full U1, a global symmetry U1, the dynamics changes locally, so it's a very dramatic operation. If you gauge a discrete subgroup, then the dynamics does not change locally, so this is a much milder operation. In particular, because all these theories, SO3+, SO3-, and SU2 have the same local dynamics, it's a natural guess that gauging will move us between these theories, and that's correct. So let's study a little bit of gauging. Let's say that we start with the SU2 theory. Sorry, first of all, what's gauging? Gauging, definition, it's summing, gauging a symmetry is summing over backgrounds of the symmetry. In the path integral formulation. Now, summing over some background in the path integral means that you have made the background dynamical. You go from having a background field to a dynamical object. So let's study the gauging. Of the set to electric in SG2. Okay, I'm going to look at the partition function. That's always a good thing to look at. So I'm going to sum over bundles with W2. Okay. Sorry. I'm going to sum over B2s, B electric. Of the partition function of SU2 with coupling tau and background B electric. I should say, typically, it's convenient to add some external normalization. When you gauge, you divide by the volume of the gauge group. I'm not doing that, it's not very important. But you can do it if you want. Let me not do it, doesn't matter. All right, so let's expand this. We know what this is. Well, we knew it, at least, at some point. Let me write it again. So this is the sum over B's as cohomology classes of the sum over bundles that have W2 of the bundle equal to B of the path integral over connections on those bundles and the other fields and the action in this case. Okay. All I did is take the standard expression for the partition function I wrote before and summing over all backgrounds. Now, if we look at the structure of this sum, we are saying, let's forget about this, we are summing over all bundles satisfying some conditions, W2 equal to B, and there we are summing over the Bs. That's the same thing as summing over all bundles, imposing no conditions. Right? You take the sum with something set to 0, something set to 1, something set to 2, and then you sum over all those. You are summing with unrestricted values. So that's what I'm doing here. And then I have the partition function. And of course, this is the partition function of the SO3 plus theory, coupling tau and 0 background. Okay, so this is how I get SO3 plus from SU2. It turns out that you can also get SO3 minus from SU2 from a gauging. So let me introduce a new operation. I'm going to call tau acting on SU2 theory. Defined as follows. I take the SU2 theory and I couple it to an SPT that I'm going to define now. Now, what's an SPT? The letters mean symmetry protected topological phase. That probably doesn't mean much. This is also synonym for all purposes as an invertible theory, which probably doesn't mean much. And it's synonymous with anomaly theory. And this should mean a little bit more to you at this point. I just want to flash the words. Those are words that are used in the literature. They don't matter. There's some definition. What this is a classical theory. So something that does not depend on anything but background fields. But it does depend on background fields. On, in this case, the background fields of the SU2 theory, so it depends on B. Okay, so it's one of the theories that we saw, for example, when we were studying the mixed anomaly in Maxwell theory. If you remember, we went to 5 dimensions and we constructed a theory that was almost classical. It didn't have any oscillating fields, but the action was non-trivial. It depended on the background fields. So this is the same sort of object. In this case, the SPT is an object whose action, so let's say the partition function of the SPT, in this case it's a 4-dimensional SPT, is simply the exponential, there's no path integral, the exponential of minus the integral over your 4 manifold of the Pontryagin square of B divided by 2, and okay, conventions. This is pi I over 2. Okay. So we saw the Pontryagin square already in defining the SO3 minus theory, so it's good that this appears. At the time, I wrote this as -1 to the integral of Pontryagin square over 2, but of course, that's the same expression. Well, not of course. There was a question yesterday, which was a good question. What I really mean by this is this. Right, so there's a partition function of this theory. So if I want to construct the partition function of my SU2 theory after acting with tau, I just take the product of the two partition functions. These are really two decoupled theories. So basically what I'm adding here is a counter term. When I was working in Maxwell theory, I told you, well, I'm working modulo counter terms, and that's fine as long as you don't gauge. Once you start gauging, one thing we saw is that the counter terms can change which things you can gauge, how gauging behaves. So this is one of those cases. Okay, so I'm going to define SU2 0 to be the SU2 theory from before. That is without the counter term. And SU21, I define to be putting this counter term, so tau on SU2 0. Okay. If you're in a spin manifold, if you act with tau twice, you get the identity. I'm not going to prove that. Okay, so now it's easy. So now note that gauging B2E in the SU21 theory. So once I have added this counter term, it is this, the sum over B, I'm sorry, the 2, of sum over bundles that have W2 equal to B2 of E, of the path integral, of the action. And now with this extra counter term, which is -1 to the integral of Pontryagin square of B divided by 2. But of course, here I have the same sort of argument, right? This is the same as the sum over all bundles, unrestricted. So I have the sum over all bundles. And now with a factor, which is -1 to the Pontryagin square of the characteristic class of the bundle over 2. So that's indeed the partition function of the SO3 minus theory at 0 background. Okay, so there's much more you can play with here. At this point, you can do quite a few calculations which are interesting and involved. If you want to look at those, you can look at this paper by Kaidi, Safrir, and Cheng. And the references. For example, one exercise I encourage you to try, it's interesting to make sure you understand these things properly. Show that gauging the set to magnetic in SO3 plus gives you SU2. So give it a go. And if you have any questions, I'm more than happy to discuss. This is, by the way, a standard phenomenon. I'm not going to make a huge emphasis on this. But I just proved to you that if you start with SU2 and you gauge the one-form symmetry, you get SO3 plus. If I now gauge the symmetry that you have in SO3 plus, you go back to SU2. So this phenomenon that you gauge once, you gauge twice, and you go back to original theory, it's very widespread. And it comes from the fact, essentially, that gauging is some sort of Fourier transform. Okay. Any questions? Yeah.
If we wanted to get the partition function of the theory with the new background field,
Yeah.
we would have to add like an e to the
Yeah.
TI.
Yeah, that's correct. Yeah, exactly. That's a very good point. Very often what you want to do is to put a background field at the end. And to do that, what you do is you modify this by adding a counter term that looks a bit like, in this case, -1 to BBM, essentially. So my mysterious Fourier transform words connect with this. Think of this as e to the IPX. Yeah. Very good. Any other questions? Okay, so of course there's much more that you can say about non-abelian theories. But my personal understanding of this topic is that once you understand the Maxwell theory well enough, many things of these ones are just group theory in the end. So you have to think about roots, co-roots, and so on. But the basics of the physics are already in Maxwell theory. What I want to discuss next are anomalies, or more precisely, the modern understanding of anomalies. Because modern will get old at some point. Sometimes we call this the Diophrid understanding of anomalies. For reasons that will become clear in a second. If you want to understand the sort of the classical picture of anomalies, which is perfectly correct, just a little bit more restricted, I recommend very highly these lectures. How are they called? An Introduction to Anomalies. So for the classical picture. Anomalies by Luis Albert Gomez. There's also a nice review by Adel Bilal, which unfortunately I didn't write the reference, but you can find it easily. And if you don't, do ask me. So if you read these two things, you probably will understand everything as it was understood in the 90s or so. 80s, I would say, perhaps. So I'm going to summarize this story very quickly. Maybe it's good to know, how many of you have studied anomalies, as in triangle diagrams and so on? How many of you haven't? Okay, that's a fair bit. All right. So I'm afraid my discussion will leave you a little bit unhappy because I'm going to skip over everything that's in textbooks, basically. But luckily, that's in textbooks, so you can learn about it. So let's think of it in this way. Let's say that we have a partition function, and sorry, and one thing I should say, not be mostly focusing on fermions. And this is because these are typically the most important sort of anomalies, but of course there's others. But let me think about fermions, because the structure is very pretty and it generalizes to a general story. So then what you have for fermions is that you can construct some partial path integral, let me call it like this, that depends on your field A by taking the integral over the fermion degrees of freedom of the exponential of the Dirac operator coupled to A. So this is the definition. The idea here is that we have a theory with fermions and some field that we are going to try to gauge. And first, we compute the path integral over the fermions. The way the fermions couple to the field, say the U1 connection of electromagnetism, is through the Dirac operator, an action that, okay. So we need to be careful, the integral of the Dirac operator. All right, so you have an action like this, and I'm going to do the path integral in two stages. First, the fermions. That gives me an object that depends on the A's, and then, if I can, I will try to do the integral over the A's. So an anomaly, from this classical understanding, is an obstruction to doing the integrals over the A's. You can always do the integral over the fermions. Perhaps, not to confuse you, I apologize. Let me write a bit more generally, S depending on the fermions and A. But this is going to be, of course, the integral of something like phi bar Dirac operator of A, phi bar plus other terms. Okay, that's a bit clearer. All right, and let's think about this as a function of the possible A's. So consider the space of all connections A. So just to make this picture, this geometric picture prettier and easier to understand, I will assume that A is a connection on some G bundle, and G is continuous. So the thing to have in mind is some non-abelian theory, for example, with some Lie group SU2 or SO3 or something. So we have the space of all the connections we can put in some fixed four manifold. This is going to be a huge space, infinite dimensional one. Let me give it a name. I'm going to define M to be the space of connections modulo gauge transformations. So of course this is infinite dimensional, but let me draw a picture, just to have some picture in mind. I have some space M, and over this space I have a function set of A that depends on the connection. I use the word function, that's a bit of a lie. In general, it won't be a function, in a way that I will explain in a second. But locally it will be a function, so something that if you give me a point, it produces some partition function, some set. Now, if I want to integrate over this manifold, which is what I'm doing when I do the path integral, it better be that this is an actual function. I can integrate functions over manifolds. The thing I cannot integrate is non-trivial line bundles. So an anomaly from this point of view holonomies for set of A on M. So what does this mean? If I want to do an integral, I want to have an actual value of Z here, a different value here, and I do the integral as usual. It's an integral over some manifold, infinite dimensional, but some manifold. But if I have a holonomies, I cannot properly define the integrand as I go around. If this set changes, then I cannot define the integral properly. In some cases, even worse. In some cases, the only definition that one could potentially concoct gives you 0. So if the path integral is 0, you're in trouble. So I will explain an example of this in a minute. Okay. And there's two ways in which this can happen. Two kinds of anomalies. If there are holonomies locally on M, we call this a perturbative anomaly. So more geometrically, the set of a bundle has curvature. Okay, so what does this mean? A little loop in this space is going from A to some gauge transform of A. Right, this is the space modulo gauge transformation, so a little loop can take me to a gauge transform. If in taking a small gauge transformation, my set changes, that's the standard definition of an anomaly. Unpacking, we are saying something like set of A plus d lambda for some small lambda is some phase, the holonomy, times set of A. So in this geometric picture, this statement gets translated to the fact that if I do a little loop in this space, I pick up a holonomy, and that means geometrically that this bundle has curvature. Right? Curvature is the thing that gives you holonomies locally. Is this a familiar statement? I think I've used it before in the lectures, so hopefully it's fine. What I'm saying is, if you construct a family of connections such that you start and end on two field configurations that are related by a gauge transformation, you can pick up a phase. So think of this process as a smooth process. Not just doing all the gauge transformation at once, but connecting these two field configurations.
Traditional points of these manifolds are not supposed to be connected by a gauge transformation.
Most points are not connected by gauge transformations. When I quotient, I throw away that information. So most connections on a bundle are not gauge related, right?
So if I perform a gauge transformation, I'm staying on.
You stay on the same point, exactly. The idea is that if I do a little loop like this, I can, in the covering space, be going from one field to a gauge transform of the field. If I pick up a phase in that, it means that I cannot consistently define the phase of set under gauge transformations. There's no unique value for A plus d lambda. You could say A plus d lambda is because I'm staying on the same point. It's just the original value. That's a valid definition. But the valid definition is no, I'm going to parallel transport my set around this bundle, and I end on set of A plus d lambda. So for the same point, I get two values with different phases. Yeah? There's abstraction. The abstraction to integrating. Of course, there's nothing wrong with having a bundle with curvature, that's fine, but you cannot integrate over a section of this bundle. Yeah, very good. But that's not the only thing that can happen. So just to say, this is a fancy way of saying something that you have, most of you have seen. So these are the perturbative anomalies that you compute calculating the triangle diagrams. So from this point of view, the triangle diagrams are giving you the curvature of this bundle. If you want to understand the connection, you can go to the lectures by Luis, and he explains this very well. But this is not the only option. You could also have, say you have some two cycle to make my life easy, and you go around this, so this one cycle in this manifold, Imagine that it has a little bit of topology. And as you go around, you pick up a face. This can happen even if your bundle is flat. So if the bundle is flat, but there are still anomalies, so there are still holonomies, we say that we have a non-perturbative anomaly. This is often also called the global anomaly. I will try to avoid the word global, because in this context, global can mean at least 3 different things. So I'm going to try to use non-perturbative anomaly for this phenomenon. Okay. I try to compute the path integral. I go around the loop. There's no local curvature, so all my triangle diagrams vanish. But still, I find that there's some phase that appears as I go around. I still cannot define my path integral, so I'm still in trouble. But these ones are much harder to detect. So we'll mostly be talking about these ones to start with. Any questions? Okay. So one important observation is that if you have a field which is gappable, I'll explain this in a second, then it does not contribute to anomaly. Okay, so here to specify gappable preserving the symmetry. So what does this mean? If you have a field for which you can turn on a mass, say, and give it a mass in such a way that you don't break the symmetry, then this does not affect the anomaly. It does not enter in those considerations. And the reason is basically that this calculation is mostly topological. We're talking about curvatures of the bundle and holonomies of the bundle. So if I have something to which I can give an arbitrary mass, it cannot affect these results. Either they are there or not, but giving a mass cannot change them. So this is an important corollary. Which is that in Lagrangian theories, I don't know how to prove this in general for non-Lagrangian theories. So in Lagrangian theories, for a field phi, for some fermion, the anomaly is a phase. Okay, so what's the idea here? If you have a field in some representation R of the group G, then you can introduce some field, I don't know, phi tilde in R bar of G. You can think of the partition function of the field phi under A. And because of the factors in the Euclidean, you can convince yourself that this is the complex conjugate of the factor, of the partition function of phi tilde. Okay, this is basically because you have the conjugate representation. There's an I which introduces with a minus gives you the complex conjugation. So write the action and you'll see it. So this implies that the system phi tilde has no anomaly. Why? Because you can introduce a mass term, which is this one. That clearly is a mass term that does not break the symmetry. You always have a singlet between R and R bar. So this observation together with this one implies that Z phi times Z phi tilde, which is Z phi modulus squared, has to be equal to 1. So it has to be well defined. Sorry. To be well defined. So there I wasn't being very careful about what can happen to Z. Could be as multiplied by 5 as you go around, who knows. But this argument shows you that the only thing that can happen in Lagrangian theory is that it picks up a phase. That's because the modulus of Z is well defined because it's the partition function of this combined system in which I can gap all the matter. Okay. So the combined system does not have an anomaly, and therefore multiplying the partition function, these two things are decoupled, tells me that this thing is well defined, and therefore the phase is well defined. So the phase is the only possible for anomaly. Any questions about this argument? There are a couple of subtleties that I skipped over. If you want to look at those subtleties, you can look at the paper by Witten as a ref. Paper by Witten, which is okay. Let me start with the local anomalies. I won't say much, the perturbative anomalies. So this is a fact that I'm not going to explain. The curvature of the bundle well, the curvature of the bundle, if you think of the bundle as a line bundle, is going to be a two-form. So I'm going to pull back this two-form to space-time to construct some object, which many of you probably know is the anomaly polynomial. Often written by I, it's a 6 form, and this is the characteristic class of the bundle times the error of genus of the tangent bundle. So this is a D plus 2 object, and this is restricted to D plus 2 dimensions. So very often the way the presentation you will see in books is that they start with this sort of diagram, they prove non-conservation of currents, they show that that can all be neatly packaged using something known as anomaly descent in some group representation data that happens to be computed by this quantity here, that they call the anomaly polynomial. historically, that's the way things went, and then people realized that this can be also understood as a curvature in a bundle. I'm starting from there and just stating that all that is true. My interest is in what happens when this polynomial vanishes. So when we have flat bundles that they still have holonomy. So I'm going to assume for the rest of the lecture that ID plus 2 is equal to 0. Right. So, of course, the most well-known example of this was an anomaly that Witten found. Just going to sketch his argument. For the details, you can go to his original paper. This is an example of a theory. Well, let me write the theory first. So theory, SG2 gauge theory. With a Weil fermion in the fundamental. What Witten found is that this theory, if I actually gauge the SG2, is inconsistent. It's not it doesn't make sense. And the way he showed it, basically, is by making that picture precise. He constructed a family of connections that made a loop in this space M. And he showed that the partition function picks a minus sign as you go around this loop. So let's try to understand first what the loop is. So in general, for this kind of analysis, we choose my 4 manifold to be R4, Euclidean. And I'm going to assume that gauge transformations go to the identity at infinity. This is not really much of an assumption. If it doesn't go to identity in infinity, it's just not a gauge transformation. So when I'm talking about gauge transformations, the things I'm going to quotient by, they have to go to 1 at infinity. Now you have some function G from R4 to SU2 to some group G with G at infinity going to 1. This is specified by a function. I'm still going to call it G, put a hat if you want, from S4 to G. So the idea here is that you can take infinity and compactify to a point, because all the image of this function is the identity. Okay, so let's study which kind of gauge transformations we have in R4 for a generic group G. Such maps up to homotopy, so up to the formations, are classified by pi 4 of G. Now, if I want to see a phenomenon like that, a holonomy, and if I have no curvature, it means that if I can deform my path to the identity, I won't see any anomalies. It must be that I have some G that's in a non-trivial class in pi 4 to the G, in pi 4 of G. So I'm going to choose. So what we did, choose G equal to SU2. And in this case, you have pi 4 of SU2. This is pi 4 of S3. And mathematicians have computed this already for some reason. And this is it. So there's indeed a gauge transformation, which is homotopically non-trivial. I cannot deform it to the identity. Just to mention, you can replace here SG2 by any symplectic group, and that still holds. So there are some easy generalizations here. Okay, so data space M is my A's up to gauge transformation. So if I start with an A and I act with a generator, I still get the same thing. So I'm going to choose G to be a generator of pi 4 of SG2. And I'm going to denote AG to be the gauge transform of A, so that's up to some conventions. This thing. Okay, so A and AG give me the same point in M. There's one point in M. Now I want to construct a loop between them. So pick some function. Doesn't matter which one. F of t such that, so this is defined in an interval, and it's a real function, such that f of 0 is 0, and f of 1 is 1. So to define the loop, we define the loop, my set of points in M, to be a t. So I think I call it a t. Yeah. Which is formally the transform of 0 times, sorry, it's f of t times the gauge transform of 0. So more concretely, that's f of t and, okay, maybe I should have put this. And then g minus 1 dg. Okay. I emphasize, despite the appearance, this factor here is very important. It tells me that this is only a gauge transformation whenever f of t is an integer. Well, it's 0 or 1, really. So at the endpoints of this, for some monotonic function, I have gauge transformations, but otherwise I don't. So I have a loop like that one. So there's a global anomaly. No, there's a non-perturbative anomaly. If set of A at 1, defined by parallel transport, so in that way. set of A0 is different from 1. Any questions so far? Right, so in the SU2 case, well, let me do it in general. In general, for a real fermion, what do I mean by this? This is a fermion that, if you take into account both the Lorentz transformation and the gauge group transformations, is in a real representation. So in the product group of Lorentz times your G, you are in a real representation. So you have a fermion in this representation, and you try to write a mass term, this thing identically vanishes because of the anti-commutation relation of the of the Grassmann variables. Yeah. Mhm. Must have what?
In order to look over M,
Mhm.
for each t different from 0, 1, I must have a different gauge configuration for each non-equivalent one.
Yeah, and these are non-equivalent because of the f of t. Say f of t is t. This is only a gauge transformation where the coefficient is 1 or 0. A gauge transformation is by definition, sorry, something that is pure gauge is by definition something that can be constructed by putting a equal to 0 here. Mhm. Yeah, so if I put it 1/2 in front, that's not a gauge transformation. Yeah. And remember, maybe at some point we were doing these large gauge transformations of U1. And we could measure them by computing the winding number. That was an integer. That's related to the fact that this comes from, there's some very precise coefficients in here. Yeah, very good. Any other questions? Okay. So in general, you have a real fermion. You could, in principle, write a mass term that does not break the symmetry G. This is Lorentz invariant and gauge invariant, and G invariant, if you write the indices. But you will find that it identically vanishes, because these variables are Grassmannian. But you can introduce 2. So both copies of the original one. So basically, I double my system. I consider my system twice, and I call one of them psi 1 and the other one psi 2. Then I can introduce a mass term like this, and this is not 0. So in the SU2 case, my fermion is a real fermion in that sense. And this implies that I cannot give it a mass, it's not gappable, but twice the system is gappable. If I consider the same system twice, so if you want SU2 with 2 fermions, the thing is gappable. So this implies that the partition function, so the anomaly, can only be a sign, so plus or minus 1. And the idea is as before. Let's see if I still have the argument. Yeah. The idea is as before, but now my new fermion is not in the conjugate representation, it's in the same representation. So I have that twice my partition function S squared, not with the bars, but really squared, has to be well defined, and that means that the possible ambiguity is a sign. All right. So let me draw a picture of what's going on here. I have my original space, which is S4. I construct a cylinder parameterized by T, and I end up with S4. Here I start with a gauge configuration, which is 0, say. And I do this family of gauge transformations, so I end up with a configuration which is the gauge transform of A, so that's 0 gauge transform, which is G minus 1 dg. Now, because these two things are gauge transforms of each other, I can glue them together. So what I have is a non-trivial bundle, but the gluing can be done by gauge transformation in my symmetry group in G. So I can define an object, which is a 5-dimensional manifold, where these slices here are S4s, and then there's an S1 as I go around. So this is known as the mapping torus. Now, because in going from one end to the other, or going around the mapping torus, I pick up a gauge transformation, that means that there has to be some field strength somewhere inside. If you want, despite that being a gauge transformation at the endpoints, it's not a gauge transformation generically, so I have some varying physical field. If I have some varying A, that means there's some sort of field strength somewhere in the middle. So we have some sort of F here, some non-trivial bundle in general. And this tells us that there's some non-trivial bundle here. So we have this sort of torus with a non-trivial bundle on top. And a sign that we need to compute. So Witten argued that the sign, so like this, set of A1 is set of A0 times minus 1 to the mod 2 index of, let me call its name, of phi coupled to E. Right, so what's mod 2 index? It's a fancy name for the dimension of the kernel of the Dirac operator coupled to this bundle, mod 2. So we are in 5 dimensions. Construct the Dirac operator in 5 dimensions. Compute the kernel of the Dirac operator, that is, how many 0 modes does this Dirac operator have. So happens, you can check using Clifford algebras that in 5 dimensions for this kind of real fermions, the kernel modulo 2 is an invariant, is a deformation invariant. So the dimension of the kernel modulo 2 is an invariant, it's 0 or 1. So if you take minus 1 to this, you end up with the actual sign that you have here. So we'll see this generalized when we start studying the die-free picture of anomalies, which is very much inspired by this. But this is what it is in general. So let me call this I. And then you have, by calculation that you have to do, this is not straightforward, in this configuration, I is 1 mod 2. Okay. So this general formula tells you that there is the potential for the sign to change. But to actually see that it changes, you have to compute the precise form of this bundle, compute the structure of zero modes, and see that you actually do have a zero mode. That will take me too long, but you can go to a paper by Witten, that I cited somewhere, the one about the SU2 anomaly, and the details are all there. Okay.
Sorry, could you please repeat why you apply an SU2 with fundamental size with
Yeah, the fundamental of SU2 is pseudo-real, but this is a Weyl fermion in the Euclidean, which is a pseudo-real representation. So in the Euclidean, the Lorentz group is SU2 times SU2. A Weyl fermion is a fundamental one of those SU2s. So you have pseudo-real of one SU2, the Lorentz, times pseudo-real of the internal SU2, the gauge one. So pseudo-real times pseudo-real, that's real representation. Yeah, very good. Any other questions?
Can you please repeat the structure of the bundle E?
I didn't really tell you the construction, but intuitively what's going on is that I have a family of connections here, A of t. You can view this as the component of A when promoted to a 5-dimensional bundle. And then you have the components of A along the S4, and one extra component that comes from the family, from the way I have defined this family of S4s. So now I have an A with 5 components. And once I have an A very concrete A, I can start computing, well, that defines a bundle for me. I have a connection. So it's in too many words, I don't know if it's clear. So the important thing in going from an A in 4 dimensions to an A in 5 dimensions is that you have to give it one extra component for the A. The extra component is in the T direction. So I didn't choose this notation randomly. It's because if you look carefully at this family of connections, how it promotes to a 5-dimensional picture, this expression is giving you the component of A in that direction.
So basically, different slices of this bundle,
Mhm.
different configuration,
Mhm.
and the first one and the last one have the same gauge configuration. That's why we have
Up to gauge transformations. So the A itself is different, but it's a gauge transform of the original. It's a gauge transform of 0. Yeah. And in the middle is not a gauge transform of 0. Mhm. Yeah, very good. Any other questions? Okay, so maybe just to finish, let me say why this is a problem. I know I was a little bit fast here. I do encourage you to read Witten's paper. This is not a straightforward computation. It will take me too long. But hopefully the idea is clear. And we'll generalize it to Diefried in the last lecture. But let me say why this is a problem. If you have, again, this space M of connections that I'm integrating over, we have found that you can take a little loop and pick up a -1 monodromy. Hold on. So let's think about the path integral. Imagine that we try to gauge this SU2 theory, now that we have found out that there are minus signs. So this will be the integral over all connections, not modulo gauge transformations, at all connections of dA e to the minus s Jan-Mills of A, so the Jan-Mills term, times d, how do I call it? Z of A. That's the integral we want to do, right? We have the background field A, we give it some action, the Jan-Mills action for A, and we integrate over A. This is the same thing as the original path integral, because ZA is already the integral over the fermions. So we do it in stages. First, we did the integral over the fermions, and we got this Z, and we want to gauge A, we sum over the A's with some action. Yeah? So the calculation above implies, assuming that you believe this, that for any A, you do a gauge transform, you get a minus sign. That's basically, if you want a quick argument, I did it for 0, but because you can reach any connection from 0 smoothly, and this is a sign, a plus or a minus, it has to stay the same sign for every connection. Yeah. So I can write this path integral, the path integral of my theory, as an integral over M. Well, maybe let me write it a bit differently. Integral over all connections, modulo large ones, modulo large gauge transformations, G. So I start with this set of all connections, and then every connection will have a twin, which is the large gauge transform of that connection. So I'm going to pick one representative of that pair. Okay? Just formally, I don't need to do the details. You have dA, e to the minus s, Jan-Mil of A. Jan-Mil's action itself is invariant. Enter the gauge transformation. The measure is invariant. I don't have any local anomaly. And then what I get, yes, undoing the folding in the integral, is I can take set A and set A gauge transform. So this is almost the tautology. All I'm saying is that I can do the sum over everything, or the sum over half, and then in each term in the sum, I include both terms. But now, of course, because of this relation, this thing is 0. And so I get that the partition function itself is 0. And the same is true if you insert any gauge invariant operator So if you want to compute the correlator of some operator, which is gauge invariant, let me call it X, some operator, this is going to be the partition function with an X inside, modulo the partition function, so this is going to be 0 over 0. So at this point, we're in serious trouble. So this theory cannot really make sense. It's not a quantum theory that we can use for calculating anything. Okay, let's just stop here.